Okay, let's start. Good morning. So this week is about the fundamental theorem of calculus, finally. One of the core ideas of this class. But before the fundamental theorem of calculus, we need to define Riemann integration, which, really is not that important in a sense, because if you look at the history of things, the fundamental theorem of calculus was proved by the advisors of Isaac Newton, really. And Riemann was born about 100 years later, Newton. So in a sense, fundamental theorem of calculus predates Riemann integrals by 100 years. So when we're sort of learning these type of things for the first time in undergraduate education, we have this, idea that everything is pristine and stuff like that. And we define the Riemann integral, we define differentiation, and then we define we state the theorem, and then we prove it. But in reality, it works the other way around. People have an idea as to what should be the case, and then they define things so that the thing that should be true is true. Okay, it's the other way around, which is a funny idea. So as I understand, Isaac Newton's advisors, I think Darboux, one of them, the way he was thinking of integrals was sort of like a geometric way, which was, you have this function and the integral should be the area underneath. Okay, that's what he was thinking. At that stage, they weren't really interested in formalizing these ideas. And if you think about it, in fact, even when I'm saying they proved it, they proved the fundamental theorem of calculus, what they meant by a proof is quite different from what we mean by a proof now. Of course, they are compatible, and we attribute these ideas to these people, but everything is relative to each other in a sense. And in sort of like math, we tend to forget the historical context of things happening. But anyway, so in Riemann integrals, we first consider closed and bounded intervals again. And we had the set IP of I. This was the set of all finite interval partitions of I. So the idea is that you have here your interval, and you decompose it in a sense. Okay, so for instance, one partition could be something like this. That's a partition. The way I described it is that the elements of the partition are these line segments, closed and bounded intervals. But because we're looking at partitions of an interval into finitely many subintervals, you can also look at the cut points here. Okay? And any finite interval partition of the interval is completely determined by this list of points and vice versa. Okay? So maybe I should give an example about this. So let's draw it here. So for instance, consider I to be the unit interval 0, 1. So in my notation, for instance, I can look at this. P, curly P, is, let's say, the closed interval from 0 to 1/3, and then 1/3 to 1/2, and then 1/2 to 1. Okay, that's a finite interval partition. So elements of IP of I are collections of intervals like this. They're not disjoint, of course, because the interval is connected, right? But they intersect only at the cut points. And so I can think of the partition like this, or I can think of the cut points. Namely, it's this array of numbers, or list of numbers. Okay? So you can think of it like this or like this. In one dimensions, of course, this is fine, but in higher dimensions, things get more complicated, and it becomes more complicated to sort of describe a partition based on where different pixels are cut. Okay? And we had these two ideas, these two sort of operators, if you want, lower Darboux sum and upper Darboux sum. We also defined something called the Riemann sum, but that requires sampling points on each of these cells. And writing this Riemann sum as sort of like a functional like this is complicated a little bit. So I'm going to leave that to you as an exercise. Riemann sum as a functional. So you should give to it some bounded function on the interval. And now you need to define this new part, because not only do you need a partition, but also you need to be able to sample points depending on the partition. So maybe sampled interval partitions. So maybe you need to define this new set, and then it's going to be a function like this. It's not super important. What is important is that this Riemann sum is going to be lower bounded by the lower Darboux sum and upper bounded by the upper Darboux sum. And how do you do this? All of these are based on the same idea. We're going to approximate the function, or rather its integral, using a bunch of rectangles. Okay? And so to compute the area of a rectangle, you need some width information and you need some height information. So basically what we're doing is the following. We're saying, oh, this integral basically should be something like this. Rectangles are, and here this is the height of r times the width of r. Okay. Of course, what exactly this height is depends, and there are multiple different sort of implementations of this idea, but they're all sort of like based on this. Okay. Maybe if you have time, or maybe in the problem sets, you're going to see something called the steel chest integral, where you sort of change this width, but they're all the same. And so each of these cells, each of these pixels in my partition is an interval, which means that I can look at the length. Okay. And then what I can do is, on this pixel, I can look at the infimum of f. I know this exists, and it's a number, because I assumed that f is bounded. Okay. And I can do the same thing with the sup, of course. So maybe let's do an example, continuing from this, to compute the lower and upper Darboux sums of a certain function. I'm going to continue from this. I want to write things there, so I think I'm going to continue from here. Let me read this as well. There is this refinement idea that I'm going to discuss in a second as well. But let's first understand this lower and upper Darboux sums as numbers. Okay, so continuing from here. Let's say my function is defined by, let's say, x. X goes to x, identity function, so the diagonal function. Okay, so let's say that I'm trying to compute the lower Darboux sum of this function relative to this partition. That's valid, I should be able to do this. And so I have three elements, even though I wrote it like this. I have three guys over here. Okay, so this is infimum of this times its length. What is the length of this? 1/3. Huh? 1/3. Yeah, 1/3. It does make sense, right? Because if the size of a pixel is large, it should contribute more to the average, in a sense. And then I have inf from 1/3 to 1/2 of f of x, like this, times the length of this is 3/6 minus 2/6, which is 1/6. And then inf, where x varies from 1/2 to 1 of f of x, times the length of this, which is 1/2. Okay, now I can evaluate all this stuff. F of x, after all, is just x. And it's a strictly increasing function, which means that this is going to be 0. This is going to be 1/3. This is going to be 1/2. Which means that in total, the lower Darboux sum of this function relative to this partition is going to be 1/18 plus 1/4. This goes away. And then if you wanted, you could simplify this and stuff like that. Okay. Any questions about this? You can do the same thing with the upper Darboux sums. If I were to have the upper Darboux sum for the same function, this would be 1/3 because it's strictly increasing. This would be 1/2. This would be 1. So you see the upper Darboux sum would be bounding from above the lower Darboux sum relative to the same partition. But the point of all this, of course, is that you fix the f, you fix the function that you're trying to integrate, and you do something with the partitions. This is where all the bizarre things start to happen. Okay, that's why I'm sort of trying to make you more comfortable with this idea of a partition. And so what is important, for instance, here is, when it comes to partitions, is the notion of refinement. Okay, so for instance, here we have this partition P. But I can look at a refinement of it, maybe the following. This is my interval from 0 to 1. I have the partition P, so 1/2, and then 1/3 is somewhere here. Okay, so this is the first pixel of P. This is the second pixel. This is the third pixel. This was my P. For a refinement, if I'm trying to refine P by some other partition Q, well, the same cut points are going to be preserved, because the pixels, when you're refining a partition, have to decrease, okay? They have to get smaller. So this cut point is going to be here. This cut point is going to be there. But maybe there are more cut points. Maybe somewhere here, 1/4, let's say, and then 3/4. So that's a refinement. Refinement. Okay. And so, for instance, writing this out explicitly, I would have something like this: 0 to 1/4. 1/4 to 1/3, 1/3 to 1/2, 1/2 to 3/4, and then finally 3/4 to 1. Okay? The important thing here, of course, is that when you think about it, generally speaking, the pixels of a partition should have smaller length. Okay? So for instance, in P, we had this cell, this pixel. And when I switched over to Q, the pixel, this particular pixel, I didn't do anything. Okay? But there are other sort of like pixels that I made smaller. I cut into pieces. So in a sense, in this limiting procedure that's going to define Riemann integration, what should happen is that ultimately I should keep refining my partitions in such a way that the length of all of the pixels ultimately decay to 0. Okay? So it shouldn't be the case that I keep refining this pixel over here and I don't do anything here. This should decay too. I should keep cutting this eventually as well. Any questions about this? Okay. And so to formalize this idea, I thought it would be good to give a name to the structure that this IP of I has, given by the notion of refinement. And that is the notion of a directed set. So here's the definition. A directed set is a pair, A comma this curly less than or equal to if you want, where A is a set and less than or equal to is a relation of A satisfying two properties. Okay, so it's a subset of A times A. For any, let's say, A, B, and C in A, if A is less than B and B is less than C, then A is less than C. This is also one part of this notion of an equivalence relation, but it's a different type of, so we're going to define a different property. So this is the transitivity property. Okay. The second property is the important one. For any A and B, there's a C such that A is less than or equal to C and B is less than or equal to C. So maybe you are not able to compare two elements in your directed set, but at the very least you're able to take sort of like some other element that A and B compares to. That's the idea. Okay, what are examples of directed sets? Well, this is a directed set. Right, because this is the classical less than or equal to relation. If I have three non-negative integers, such that n is less than or equal to m and m is less than or equal to p, then certainly n is less than or equal to p. That's the first property. And if I were to take two integers, what is yet another integer that is greater than or equal to them? You can do that. You can take the max. Max is, I prefer the max more. Okay, so this is a directed set. Another directed set is IP of I. Okay, I'm going to leave that to you as an exercise to verify this. Exercise. Set of all finite integral partitions with this relation where I'm defining this Q is greater than P if Q refines P. Okay. Certainly this is transitive. The point of this exercise is to figure out, given any two partitions, so you need to have yet another partition that defines both of them. Maybe I should write that down. So yes?
Do directed sets have to have infinite elements?
No. No, it's like this, yeah. Given any two partitions, need another partition let's call it R that defines both. Okay. We had discussed this idea of the product of two partitions. That's sort of like one way of thinking about it. Okay. So perhaps I can give an example in this situation. For instance, consider this. You see this formalism of partitions is when you write it out, it's like, it's scary a little bit, but when you draw pictures, it's a lot more sort of pleasant, I think. So maybe P is this partition, cut in half, cut at 1/2. And then Q is, let's say, this partition. Let's use green. 1/4, 1/2. And then let's define an R. Let's use blue for that. 1/3. Okay. Now, these are three elements in IP of I, finite interval partitions. Q refines P, as you see. Okay. This pixel, I don't do anything. This pixel, I cut in half. Okay. Q refines P. P doesn't refine R, because this pixel is larger than this pixel, and this pixel is larger than this pixel. So neither one of them are comparable, and that's the problem, okay? But there is yet another partition that you can cook up that refines both of these, okay? So maybe I should write it here. Q refines P. P does not define R. R does not define P. But what I can do is this. PQRS, for instance. Let me cut at 1/2 and 1/3. Okay? Now this is a partition. And as you see, it defines both P and R. Okay? And last time we discussed how, in fact, this is the optimal partition that defines both P and R simultaneously. If there were yet another partition that defines both P and R, in fact, it would have to define this guy. So why it is optimal? In a sense, it is optimal because it is the partition with minimum cost. I'm imagining that, you know, cutting pieces in half or wherever has some like cost, and I want to sort of like achieve a common refinement without too much with the minimal cost, with the minimal amount of cuts. And so that's what the S does over here. Any question about this? whenever you get like confused about the formalism behind Riemann integrals, start drawing pictures like this and try to see. It's like, oh, this interval goes there and so on. Okay. Here's a definition. In a set X, a net or Moore-Smith sequence is a function whose input space is a directed set. Net, or people call it also Moore-Smith sequence, because it's a generalization of the notion of a sequence, is a function x bullet from A, comma, ordering to X, where the domain is a directed set. Any sequence is a net, and given a function f, bounded function, the lower and upper Darbou sums are also nets. Okay. For any f bounded, if I fix f, I have a function on the set of all interval partitions of I, taking real values, and also this guy, upper Darbou sum, are nets. Okay. Now it turns out that one can formalize the notion of a net convergence instead of sequence convergence, and it's not too complicated, but maybe I'll leave it to you in the next problem set. It's very pleasant. Let's follow the textbook and the continuation of all this stuff. All this is to say is to emphasize that what is the important thing here is this guy. Okay, that's where all the complexity comes from. Okay, so if I were to fix a bounded function f and a partition, certainly the lower Darbou sum is less than or equal to the upper Darbou sum. But what happens if I were to compare the same function, so the lower and upper Darbou sums of the same function relative to different partitions? Okay, so we need to say something about that. But even before that, I would like to understand how these functionals interact with under refinements. In other words, if I were to fix a function f, bounded function, and fix two partitions p and q, such that, let's say, p refines q, then what can I say about the corresponding lower and upper Darbou sums? P, Q, be two interval partitions. Let's say that P refines Q. Then I would like to compare the corresponding Darboux sums. So these are numbers. Which one do you think is larger? P is higher resolution, okay? P has more information because P refines Q. Pixels are smaller. So if I were to compare the lower bounds, lower Darboux sums, which one should be greater? You have 50%, 50-50 chance, right? Either this is greater or this is greater. Yeah.
The left sum is greater.
Okay, yeah. And then this should be the other way around. Okay. Well, this is true. But why is that the case? Well, what is the intuition? Well, the intuition is this, okay? So heuristic. When it comes to information theory and more complicated sort of notions in information theory, things like entropy and stuff like that, you again use things like partitions. Partitions, the notion of a partition, is also the basis of what is called conditioning and probability. Let's say Q is the trivial partition that has one pixel, which is the whole interval. Okay? It's the whole interval. That's your Q. Or maybe I should draw a picture. Like this. Okay. Let's say this is my function. It's a nice continuous function. The lower Darboux sum for Q consisting only of the interval itself, that's a valid partition, is just going to be the infimum of f times this length. Okay? Infimum of f times length of the interval. Which means that this infimum, it looks like this height. Okay, so basically you're looking at the area of this rectangle. This is the lower Darboux sum given by Q. Now, if I were to take something else, let's say I cut it here. Okay. So now I have my P. Well, in this case, it's going to be the same, of course. But let's say I cut it somewhere here. Okay. So this is my P. Let's say this is from 0 to, it looks like 2/3 approximately, and then 2/3 to 1. Okay. Now what you're going to do is, you see the inf of f restricted to this is the same inf. So you're going to look at this, the area of this rectangle. Maybe I should choose one more. Okay. Let's say 2/3 to 3/4, and then 3/4 to 1. Okay. Which means, okay. So I looked at this. Now this is the second piece. The inf looks like this guy. Okay. So you're going to look at the area of this rectangle. But then you're going to look at yet another guy, which is this final pixel. The inf is even larger. You see? So the lower Darboux sum given by this refinement is going to possibly increase. So the more you increase your resolution, the more you refine, lower Darboux sum quite possibly increases. Okay, that's the intuition. Let me check. 100%. Okay, so let's do the proof. And of course, it should work the other way around for the upper Darboux sum. Okay, so here's the proof. First, I'm going to look at a special case. Okay, so the second part is going to be an exercise. Okay. Proof for the lower Darboux sum. First, consider the case where Q consists of the interval and P has exactly 2 pixels. First, consider the case of Q with 1 large pixel and P with 2 pixels. So this is lambda to mu, let's say, midpoint, and then midpoint to rho. Okay, I claim that the lower Darboux sum associated to this guy is going to dominate the lower Darboux sum associated to Q. Well, so let's write this out. Formally, this is this sum. But then this partition only has 1 element, which means that this sum is only over 1 guy. And this just becomes the infimum of F times, what is this length? So if I is lambda to rho, what is its length? I have an interval where its left end point is lambda, right end point is rho.
Should be rho minus lambda.
So this is rho minus lambda. But then, of course, I can write rho minus lambda as, let me write it here, rho minus mu plus mu minus lambda. This is because the length of this interval is the same thing as the length of this interval plus the length of this interval. Infimum of F, let me be explicit. Lambda to rho of f of x times rho minus mu plus infimum of f of x, where x varies between lambda and rho, times mu minus lambda. Okay. Well, this was something that we had discussed all the way back in the week when we were first defining infimum and suprema, infimum and suprema. In order to go from the lower Darboux sum associated to Q to the lower Darboux sum associated to P, I have the lengths down. All I need to do is to adjust these height information. And so all I need to do is is to replace this interval, in this case, by mu comma rho. And here it's going to be lambda comma mu. But what happens if I were to take a smaller interval? What happens to the infimum over there? In other words, if I have two subsets, A and B, of the real numbers, such that A is included in B, which one is larger? The infimum of the smaller one is larger, right? That's because B is larger, quite possibly its minimum, which is basic to the infimum, is quite possibly way smaller than the infimum that you can achieve using this restricted set. Which means that if I were to replace this interval by this interval, this is going to increase quite possibly. Okay. And so that means that we have this. Times this length plus inf, where x varies in lambda to mu of f of x times mu minus lambda. And this is exactly the lower Darboux sum of f relative to p. Any questions about this? I feel like you guys are not following. Okay, you're happy with this. You're okay. Okay. Any other issues?
It checks out.
Yeah, I mean, it does, but
It's a little bit Monday to comprehend it super fast, but like it makes sense.
okay, okay. Yeah. Yeah. This is not the end of the proof, of course, because in the proof itself, it doesn't say anything about P or Q. But we can do a trick and finalize, okay? The idea is that if I can go from the 1 pixel case to 2 pixel case, and it holds, then given any two partitions, such that one refines the other one, well, instead of thinking of the refinement happening in one step, in which case multiple pixels could be cut in pieces, I can say, oh, go from the coarser pixelation to the finer pixelation. What I can do is I can pixelate 1 pixel at a time. Okay? Then apply the same reasoning. Yeah, I told you this Riemann integration, when it comes to the formal treatment, is very different from sort of like differential calculus and stuff. So for the general case, so maybe I should draw a picture. I have here my coarser pixelation, Q. And here I have the finer pixelation. What I'm saying is the following. Let's say that my coarser pixelation is something like this. Okay, it's this. In the finer pixelation, I'm going to have the same cut points. But of course, possibly I have other cut points. Maybe this, this, this. Okay? What I can do is, I can imagine there being intermediate refinements where between two consecutive steps, there's only one difference, one cut. So I can say, for instance, here's this. So maybe I use this one first. So you see, from here to there, I have a refinement. The important thing, of course, is that I only cut exactly one pixel when I'm going from here to there. Then I can perhaps cut this one, or maybe this one. It doesn't matter in which order, of course. This is still here. These two are still there. And now I'm cutting this one. And then I have one final refinement that gives me P itself. Okay? Does this make sense? Okay. The idea then is that when I'm going from the lower Darbou sum associated to this guy, all I need to do is to apply this argument to exactly this pixel, going from here to there, and say that when I pixelate this pixel into smaller pixels, or into two smaller pixels, the lower Darbou sum is going to increase. The other ones are going to contribute exactly the same, which means that the lower Darbou sum of this guy has to be bounded from above by the lower Darbou sum associated to this. Then I can keep applying the same reasoning from here to there and from here to there. Okay? So by induction, I'm going to say we're done. And by that I mean by formalizing this, which I'm going to leave to you to write in a nice manner. So this is really something that you can make a computer do. It's a finite algorithm, after all. If you have finite partitions, well, if one of them refines the other one, in finite steps, you can achieve this. Okay? So that's nice. Let me finish with one thing. If I have a bounded function, taking real values, and two partitions, then the lower Darbou sum relative to P is going to be bounded from above by the upper Darbou sum relative to Q, even though P and Q are unrelated. Lower Darbou sum of F relative to P is going to be bounded by the upper Darbou sum relative to Q. Okay. The proof of this we're going to do tomorrow because I don't want to go over. But the proof of this uses the fact that there's a common refinement for these two. Okay? There's a common refinement, this P intersection Q, or P product Q, that both refines P and Q, which means that if I were to start with this, replace P by P product Q, this is going to increase. But then the upper Darbou sum is still greater. But then if I were to replace the upper Darbou sum, into the upper Darbou sum, that refinement by this guy, it's going to increase even further. So that's how we get this. We're going to do this tomorrow because I don't want to go overboard, but that's it for today. Thank you. Okay, let's start. Good morning. I'm going to take attendance today. So we were talking about Riemann integrability. Finally, we'll be able to define what it means for a bounded function to be Riemann integrable. And then we're going to discuss certain equivalent ways of describing this Riemann integrability. Then, if we have enough time, we're going to discuss, I would like to discuss some examples. And then we would like to discuss how some of the reasonable functions, like continuous functions, differentiable functions, and so on, are integrable indeed. So as usual, we have a closed and bounded interval, I. Last time we had done this, this statement. If I have a bounded function, right, so I have the lower and upper Darboux sums associated to the function and a finite interval partition. And so we had fixed this bounded function, and we were varying the partition. We were varying the resolution with which we were seeing the function. And the statement was that if P refines Q, so this was the notation for P refines Q. So any pixel in P is included in some pixel in Q. In other words, pixels in P are much smaller compared to pixels in Q. Then, because of the boundedness property, well, the lower and upper Darboux sums are always going to be finite numbers. But in fact, the lower Darboux sum associated to the higher resolution partition is going to be larger than the lower Darboux sum associated to the coarser partition. That's also some terminology. So in this case, you would say that P is finer compared to Q, and Q is coarser compared to P. So maybe I should write it here. Compared to Q, Q is coarser. Compared to P. So as the resolution increases, the size of the pixels get closer to 0, right? Okay, so we had this. And then I said that in fact, if I were to take any two partitions, P and Q, then the lower Darboux sum associated to this P is going to be dominated by the upper Darboux sum associated to the other partition. In other words, any lower sum is bounded from above by any upper sum, and vice versa. Okay? So here's a proof of this. Well, all I'm going to do is I'm going to look at the partition that refines both P and Q. Okay? Consider R defined as P product Q. This is just the partition whose pixels are the intersections of the pixels of P and Q. Some of these, of course, could be empty, but in any event, it's still going to be a partition. Then R refines P and R refines, that's fine, Q, so that by the statements, I can start with this guy. By the previous theorem, we have that. So first I'm starting with, now I want to start with P. R refines P, which means that if I were to replace P by R, this is going to increase quite possibly. But then this is dominated by the upper Darboux sum associated to the same partition. But then if I were to replace R by Q, something coarser, okay, this upper sum is going to increase quite possibly still. And again, this is going to be a finite number. Okay. So really, once you have this result, that once you refine a partition, the difference between the upper and lower Darboux sums have to decrease, or cannot increase, let's say. It just follows from that. And given any two partitions, you can look at the common refinement of them to get something. Okay. Which means that, oh, thank you. Did we all sign this? Which means that I have this stuff, so this is a number, this is a number. If I were to look at the optimal lower Darboux sum as I'm varying the partitions P, that's going to give me a number that is bounded from above by the optimal upper Darboux sum. In other words, I have that the sup of L comma P, L of F comma P, where P varies in the interval partitions, is bounded from above by the nth of the upper Darboux sums. And again, these are finite numbers. Which suggests that the natural definition for integrability should be that this inf equals to this sup. Okay? And that is the definition. Let me denote this expression by something like an integral, but because it's a sort of it's coming from below, I'm going to denote this by integral within underbar, and I'm going to call this I f of x dx. So this is, you should read this like this. This is the lower integral of f on the interval I, and this I'm going to call the upper integral of f on the interval I. Definition. I'm going to call a bounded function Riemann integrable if this number equals this number. So in a sense, you should think of it like this. So this approximates, or this is sort of an implementation of this idea that you can exhaust the area of a shape from within, right? So if you have something like this, you can triangulate from within to get the area of this. Let's say something like this, and you start adding more triangles. Something like this, something here, and so on. And then you keep adding smaller and smaller triangles to get the area of this potato, let's say. So this corresponds to this inner integral. But you can do the same thing from without, okay? Instead of triangulating from within, you can try to start with perhaps like a rectangle, something like this. And then you can start excising pieces that you don't need. Maybe something like this. Then you get rid of this part. Then you get rid of this part and so on. The area of this shape, of this potato, should be well defined insofar as approximation from within equals the approximation from without, asymptotically. Okay, that's the intuition. And so that's the definition. Let me make this. A bounded function is Riemann integrable if, well, this equals that. So the best lower Darbou sum is the same thing as the best upper Darbou sum. I'm going to denote by R of I, comma R, the set of all Riemann integrable functions. Functions on I. And recall that this is a closed and bounded interval. For any Riemann integrable function, this common value, I'm going to call the unsigned and definite Riemann integral of f. So let me write it here. If the common value here is denoted by integral over I of f of x dx and is the unsigned and definite integral. Is the unsigned definite Riemann integral. Definite because it's on a closed and bounded interval. Now there are indefinite integrals and something called an improper integral as well, which probably we're going to discuss later. Unsigned because the way we described it, the way I defined it, this models the notion of perhaps the mass, okay? So this is sort of like your density, and you have a rod, and F gives you the density of your thing, and you're integrating, okay? So this should give you a mass. There's another interpretation of the integral, which from a physical point of view corresponds to what is called perhaps work. And in the case of the fundamental theorem of calculus, you're really using this notion of integral as work, which is the signed integral. We're going to define that later. They are related ideas. In one dimension, it's not a major issue, but in higher dimensions, it starts to become a problem. Because in higher dimensions, you have perhaps a shape. You can still talk about the scalar function on it. It's the density or the temperature, whatever. And you're looking at the average temperature or the mass or of the object or something. Or you can have a higher dimensional object and you can consider a vectorial quantity, something like a vector field. Maybe the flow of a fluid or something like that. In higher dimensions, this distinction between signed versus unsigned becomes important. In one dimensions, not that much. But technically speaking, what we defined is the unsigned integral. Okay? I want to give two examples. First, an example of a bounded function that fails to be Riemann integrable. Okay? Not all functions are Riemann integrable. And this is the standard example in this business. And in a sense, what I'm going to give you, the example, is a very nice function. Okay? And it turns out that you want to be able to integrate this function. But its Riemann integral doesn't exist. And that's why people look at other types of integrals. And in reality, once you're done with this class, probably you're not going to look into Riemann integrals in more depth. There are better integration theories. So if you keep taking more advanced analysis classes, there's yet another integration called Lebesgue integration, and that is the most common one. But okay, so here's the example. I'm going to choose I to be the closed and bounded interval, 0, 1. And let me let f to be defined like this. X goes to, let's say, 1 if x is rational, minus 1 otherwise. Of course, this is not a continuous function. It is discontinuous everywhere and stuff like that. But in a sense, it is taking exactly two values on nice sets, in a sense. So let's see that my claim is that this function, even though it is bounded, of course, but it is not Riemann integrable. And maybe I can also discuss a little bit why this Lebesgue integration would be able to handle this. So Lebesgue integral would associate the number minus 1 to this function. But Riemann integrals, we're going to see, has an issue with this. Now, let's see this, okay? If I were to fix a partition, arbitrary partition, finite interval, what are the lower and upper Darbou sums of this? Any guesses? Say again? Right, so this should be minus 1. Okay, maybe let's slow down a little bit. It is true that this is minus 1, and the upper Darbou sum is plus 1, no matter what partition you feed to this. And the idea is the following, okay? This function, it's hard to draw it, because on a dense set, right, rationals is dense, it takes the value 1, but on the complement set, the set of irrationals, which is again dense, it takes minus 1. So maybe like this. Okay. So on a computer, you wouldn't be able to sort of actually see the graph of this function, but at each rational point, it's at 1. At each irrational point, it is at minus 1. So you would see exactly two lines like this. Then I take my partition P. So it's a finite interval partition. So it is determined by finitely many cut points like this. Okay? But by the density of rationals as well as irrationals, each of these pixels, so on each of these pixels, the inf of f is going to be minus 1. And the sup of f is going to be plus 1. Okay? inf of f restricted to p is minus 1 sup of f restricted to p, this particular pixel, is plus 1. So that's my pixel. But then if I were to look at this, this is just the sum of the lengths of each of these pixels weighted according to the inf, right? So this is just going to be the sum over all pixels according to my partition times, or sum of the inf times the length. So this is minus 1 times the length of the pixel p. But this is a partition, which means that I can, so first of all, I can take this minus 1 out. And then if I were to add all of the lengths, that's going to give me 1 because the interval has length 1. So this is just minus 1. And by the same reasoning, the upper Darboux sum is going to be like this. Again, I'm adding over all pixels. This time, instead of the minus 1 as the weight, I have to use the sups of f restricted to each partition, each pixel. And now it's going to have only 1 here times the length. Again, by the same reasoning, this is going to be 1. Okay? No matter what partition I use. But then, if I were to, so that means that in this situation, for any pixelation p, this guy is minus 1. Which means that the sup of this is going to be minus 1. And the inf of this is going to be plus 1. In other words, the lower integral of this function is going to be minus 1. The upper integral is going to be plus 1. Which means that they don't match. In other words, this function is not Riemann integrable. Does this make sense? Okay. Good. Okay, I want to give some intuition, some heuristics as to why the so-called Lebesgue integral of this function is minus 1. I'm not going to define Lebesgue integration. It's a really different type of integration. And if you take an advanced class, more advanced class in analysis, you're going to spend a lot of time developing this integration according to Lebesgue. And this is basically the industry standard in math and many other situations, many other areas. Is minus 1. The idea here is that if you were to take a random point on the interval, that random point is going to be irrational. Okay? Because when you think about it, so for instance, perhaps think of it in terms of the decimal expansions. A number is rational if and only if its decimal expansion eventually starts repeating. Well, that's not a very sort of common occurrence. If you were to take a typical number, it shouldn't have any patterns, okay? That's sort of the heuristic. Of course, these things have to be proven and stuff like that, but let's not get to the proofs. I want to discuss sort of the idea behind Lebesgue and Riemann integration. So let's imagine the following situation. I have some amount of coins in my pocket, okay? And I want to figure out how much money I have, okay? So Lebesgue versus Riemann integration, or Riemann say I have, let's say, let's keep this simple. I know that I have, let's say, some amount of pennies or cents, some number of cents, and some number of quarters. And I want to figure out how much money I have in total. Riemann integration would say the following. The idea, of course, is that you cannot see all of them at the same time. Riemann integration would say the following. Okay, well, first you need to sort of start adding up. And so this is finite. What you do is, reach into your pocket, pull out one of these coins, put it aside, and record how much it is worth. And then keep doing this. Okay? Then take another coin, and so on. And so this is your time. And depending on what type of coin you're picking, either you have a cent or a quarter. Okay? So this function is something like this, perhaps. And then to figure out the total sum, of course, is to figure out the area underneath. So maybe I should be more careful. Let me draw it like this. Like this. So this height corresponds to a cent. This height corresponds to a quarter. And you keep picking, okay? And then maybe like this, and then like this. So that corresponds to the idea that the first coin that you picked turns out to be a cent, and then the next two coins turn out to be quarters, and so on. And then these two are again cents, and so on. And then to figure out the total amount of money you have, well, you just look at this integration. So you go this way. Lebesgue integration, in a sense, works the other way around. So again, let me draw the same function. Then this, that. Then these two. Lebesgue integration says the following. Instead of partitioning the domain like we were doing so far, right? We're always looking at partitions of the interval that gives us the pixelation. In a sense, pixelate the values. Okay? In other words, for Lebesgue integration, do the following. Reach into your pocket, and let's say that you're focusing on your cents. Don't pull out the coin unless you know that it's a cent. Let's say that you can sort of like feel the shape of it. Only focus on your cents. First add up your cents. After you're done, add up your quarters. Okay? This corresponds to the fact that first you look at this piece. Then you look at this piece. So for Riemann integration, you add up the values of the coins according to the order in which they appear. For Lebesgue integration, you first separate your coins into their values, then add up the clusters. You first add up and figure out how many cents you have, so that you figure out the contribution coming from cents. You set it aside. Then you figure out the contribution coming from quarters, you set it aside, and then add those two values up. Okay? Of course, in this case, it doesn't matter, but it turns out that if you just formalize this idea, Lebesgue integral of this function is valuable, is meaningful, whereas the Riemann integral doesn't quite work. Okay. So that's sort of like some heuristic. I'm not going to go any further than that when it comes to Lebesgue integration. It's really sort of, like you can imagine, it's a really different sort of theory. You might see different integration theories in problem sets, things like steel chess integral or some other types of integral. They're like similar to Riemann integration, but Lebesgue integration is really sort of, it's a different idea in a sense. It's like instead of partitioning the input space, you're partitioning the output space, and that does all the difference somehow. Of course, Lebesgue integration also has its problems and stuff like that. But for most purposes, Lebesgue integrals are very useful. Okay. Any questions? Yes?
Would you be able to repeat just really quickly what the difference was between like what one was counting cents and quarters, like in which order?
Yeah, I mean, okay, maybe let me give you a different. Okay, let's say you're a vending machine, okay? And then a customer comes to you and wants to buy something, and it's like you have to get exact change. And one thing you can do, so you have to count, right? It's like the customer is going to keep giving you coins, but you have to sort of keep track of how much the customer is giving you. One way of keeping track is a Riemannian way. You just say, I'm just going to keep track of how much the customer is paying me in a temporal fashion. Okay, first a cent, and then another cent, and then a quarter, and then another cent, and so on. I'm just going to keep adding up this way. This is the Riemannian way. The Lebesgue way is the following. First, I'm going to let the customer just put all the money in. I'm not going to evaluate. What I'm going to do is I'm going to separate the coins from the cents from the quarters. Then I'm going to have a bunch of cents and a bunch of quarters, which is, there's like this machine, you get to separate the coins according to their radii and stuff like that. So I'm going to separate the coins according to their radii without evaluating. Then I'm going to evaluate how many cents there are. That's going to give me a number. Then how many quarters there are. And that's going to give me another number. Then I'm going to add them up. Okay? Yeah. Yeah. I mean, when it comes to these kind of things, of course, it doesn't matter how you do this. But somehow, in this kind of situations, it's like they lead to sort of different ideas. Yeah. Yeah, maybe I can draw a better picture. It's the same function. For Riemann integrals, you try to approximate using rectangles like this, maybe like so. That's Riemann integration. For Lebesgue integration, you approximate using rectangles according to the output space. Then maybe this, and then maybe this. It doesn't quite make sense what I'm drawing here because it is slightly more complicated than I'm making it sound like. But I think it is sufficient. It's a sufficient approximation to say that Riemann integrals work with partitioning the input space. Lebesgue integrals work with partitioning the output space. Let's just leave it at that. Okay, so here's an exercise. It's a nice exercise because I want to relate these lower and upper Darboux sums to Riemann sums. Oh wait, even before this, what I want to do is I want to give another example where the function is Riemann integrable. Okay. So and I want to compute its integral. So let's say that f of x equals x. Okay. Now, if this guy is not Riemann integrable, then that means that this theory is not good. Okay. F of x equals x is a diagonal function. I don't even need the theory. So the integral of this should be the area underneath. And of course, if this is 1, this is 1, the area should be 1/2. Okay, so Riemann integral should exist, and it should be equal to 1/2. Or, of course, you can do the calculus thing. Right, so what is this? This is x squared divided by 2, evaluated at the endpoints from 0 to 1. And then this is 1/2 minus 0/2, which is 1/2. Okay, so I have a target. If this function is not integrable, or if it is integrable and its integral is not 1/2, that means that we did all this for nothing, okay? You might as well not have done it. Okay, so the claim is that f is Riemann integrable. And its integral dx is 1/2. Now later on, maybe not today, but tomorrow, we're going to have another theorem that's going to allow us to separate these two notions, okay? Because by now, I hope you're familiar, you're comfortable with the idea that, oh, maybe you can show that a function is Riemann integrable without actually being able to compute its integral, okay? And later on, we're going to see a couple of theorems. It's going to say things like continuous functions are Riemann integrable, and certainly this function is continuous, which means that it should be Riemann integrable. Or we can also see that monotone functions are Riemann integrable, even though they're not necessarily continuous. So we'll be able to use those to just say that, oh, this function is Riemann integrable, and if you ask me about its integral, that's a different matter and stuff like that. But for now, from only the definition that we have, we can already get this, okay? So I'm going to try to use the definition of Riemann integrability to figure out if this function is Riemann integrable, okay? So let's look at this. I'm going to fix n, let's say a positive number. And I'm going to look at this uniform partition, if you want. Uniform partition, each of whose intervals is of length 1/n. Let me call it P sub n. Okay. Now let's compute the lower and upper Darboux sums of the identity transformation, f of x equals x, relative to this nice partition. So L of f comma P sub n is this. Okay, but this is somewhat of an abstract notation. In this case, I have a very specific partition, and I can just use the endpoints. The reason why I use this notation is that if you don't use this notation, then sort of it becomes more cumbersome to write things down, at least in the abstract, because you end up needing to sort of give names to each of these cut points and stuff like that, and it becomes harder to keep track of what is actually happening. But in this case, what I can do is the following, okay? So this P is any one of these, okay? So what I can do is I can say, for instance, let's call this P sub 1, this is P sub 2, this is P sub n. These are not curly letters. So these are my pixels. Okay. So let's say I'm going from I equals 1 to n. So now my summation is over P sub i's. Okay. The infimum of the identity function on P sub 0, as P sub 1 is 0. P sub 2 is 1 over n. And in a typical pixel, it's going to be this value. Okay? So I have here this. This turns into this. Maybe I should use colors. So this infimum over one of these pixels is going to be the left endpoint. So this really is I minus 1 divided by n. And the length of this interval is 1 over n. Okay? Any questions about this? All this stuff is as simple as this, really. It's like after all the abstraction. But of course, this function is a nice function. So I need to figure out how to evaluate this sum. N squared I have in the denominator. It is constant in the dummy variable, so I can pull it out. Okay. This is the same thing as 1 over n squared. And then as I goes from 1 to n, I minus 1 goes from 0 to n minus 1. So this is this. And in fact, I don't need to write I equals 0 because that's not going to contribute anything. So it is this. But then I know the formula for this guy. 1 over n squared times n minus 1 times n divided by 2, which then means that the lower Darbou sum is exactly this guy. Okay. I'm going to leave it to you to compute in the same way that the upper Darbou sum is going to be n squared plus n divided by 2n squared. Because if you're looking at the upper Darbou sum, you're going to replace this inf by a sup, which means that in pi, instead of picking out I minus 1 divided by n, you're going to pick out the right endpoint. Okay, that's how it's going to change. So this is going to be n squared plus n divided by 2n squared. Okay. Well, then the lower integral of my function, right, the optimal this, as I'm varying the partitions, is going to be bounded by the sup of this. So as I optimize the lower Darboux sums using arbitrary partitions, this is going to quite possibly increase, but this supremum is this value. And likewise, if I were to start with the upper Darboux sum and optimize over the partitions, it's going to turn into the upper limit, upper integral. Okay? So I have a lower bound on the lower integral and an upper bound on the upper integral. Okay? But for any n, I have a p sub n, which means if I were to take the sup over this n, or sup over n of this expression, that's going to be less than or equal to this guy. And likewise, if I were to take the inf over these, that inf is going to be greater than or equal to this. So the sup of this is what? 1/2, right? Because as n goes to infinity, this converges, in fact, converges to 1/2. And likewise, this guy converges to 1/2 as n goes to infinity. And so I was able to sandwich the lower and upper integrals by the same number, which means that they have to be the same. They have to be equal to 1/2. And in particular, f is integrable. Okay. Yes?
How did you get the n minus 1 times n over 2 in,
This one? Oh, I used the formula.
Okay.
This was the sum of all integers from 1 to n minus 1.
Oh, I see. Okay.
Yeah.
Divide by n squared. Okay.
Yeah. Any questions about this? So this should be the fundamental example that you need to understand. And try doing the same thing with an arbitrary monomial, okay? Try to do x squared using the definition to understand like all of these symbols. I understand that this gets abstract when we're first defining it, and I was anticipating this. It's like the way we sort of get introduced to Riemann integrals is very different from how you actually formally consider them. Okay. Questions? I know you're sort of on the verge of burnout. I can feel it. Eventually we're going to, maybe next week or something, we're going to have the spring break and we're going to relax a little bit, but try to not get ejected, okay? Do your best. Okay, so that's it for today. Tomorrow we're going to continue. Thank you. Let's start. Good morning. So, last two classes before the break, which I think is going to be good. I'm looking forward to the break. So after the break, we again have, 1.5 weeks reserved for integral calculus. And at the end of this second week after the break, we're going to have our second midterm. My original plan was to cover the fundamental theorem of calculus before the break, but maybe it's not going to happen. It's not a major issue. Okay. So today what I'd like to do is I'd like to give certain characterizations of a function being Riemann integrable in terms of lower and upper Darboux sums and also Riemann sums. Then discuss how some of the fundamental functions that you would expect to be differentiable are differentiable. And then probably that will be it. Okay. So, yeah, before that, here's an exercise that relates Riemann sums to lower and upper Darboux sums. In a sense, so far we were using lower and upper Darboux sums because they're sort of convenient. But if you're trying to do Riemann integration, in a sense, at least for application purposes, Riemann integrals are, in a sense, nicer, even though they're slightly harder to deal with when it comes to this abstract stuff, because while lower and upper Darboux sums only require a function and a partition, for a Riemann sum, you also need a sampling function. And so here I denoted S of curly P as the set of all sampling functions for P, which means it's a set of all those functions S from the partition, which is a finite set, into the interval, such that for each pixel P, S of P is a point in the pixel P. So you're choosing one specific point from each pixel. And so once you have this Riemann sum gives you this. So this was a definition. Sum over all pixels of curly P, f of S of P times the length of P. So for Riemann sums, we needed something like this. But the relation between lower and upper Darboux sums and Riemann sums is that, first of all, of course, any Riemann sum like this is bounded from below by the lower Darboux sum of the same partition, and from above by the upper Darboux sum. But in fact, since this is the inf, so this requires the inf of the function on each of these partitions, pixels, what you can do is you can optimize your sampling function to approximate this as well as you want using Riemann sums, and likewise for the upper Darboux sum. And so the content of this exercise is that. So this is a lower bound for each such Riemann sum. And then if you were to optimize, if you were to choose your sampling function well enough, you can approximate the lower Darboux sum as close as you want using Riemann sums. Okay. So you can put in a sense, you can imagine the following. In this expression, I have these, and then I'm taking the infimum over these guys, over S of these expressions, but then I'm saying, in a sense, you can put the infimum inside the sum. If you put the infimum inside the sum, that gives you the lower Darboux sum, for instance. Okay. Yeah. And so here's a theorem that I'm actually not going to prove. I'm going to leave it as an exercise. And it might show up in the next problem set. It's very good to think about these things. It's not very complicated, but it still requires some work. So this might show up in the next problem set, which is not going to be uploaded this Friday, but next Friday. Okay, so you're not going to have a no problem set for during the break. Let f be a bounded function on the interval. Then the following are equivalents. F is Riemann integrable. Recall this was my notation for a function being Riemann integrable, because this is the set of all Riemann integrals. Maybe I should remind you. This means that the supremum of all Darboux sums as the partition varies equals to the infimum of all upper Darboux sums as again the partition varies. So So that was the basic definition, but here are, in a sense, alternative definitions. For any epsilon positive, there is a partition such that the gap between the upper and lower Darbou sum is bounded by epsilon. Third, for any epsilon, there is a, let's say, p epsilon, a partition, such that for any partition p that refines this guy, this holds. Let me denote it by this. So this should remind you a convergence sequence. For any epsilon, right, there's an n such that after this n, something happens. There's a bound. And so in the case of the set of finite interval partitions of the interval, after this n, instead of saying that, you say it refines. There's a partition such that any partition that refines this partition gives that the gap between the lower and upper Darbou sums is bounded by epsilon. Okay, fourth, there's a sequence of partitions such that the gap between the upper and lower Darbou sums for each of these guys converges to 0. Limit, as n goes to infinity, of u of f comma p sub n minus L of f comma p sub n is 0. And then here's a final one. So I want to say something about Riemann sums. For any epsilon, there is a delta such that for any partition, if each pixel in this partition has length at most delta, then I want to say something about the Riemann sum being close to some number. So I should first take a number, I guess. There is a number for any epsilon. There's a delta for any partition P if each pixel in this partition has length at most delta, then for any sampling function of the partition, the difference between the Riemann sum and this number that I chose is bounded by epsilon. Okay. So the last one is sort of like closer to this epsilon delta definition of whatever. And they are all equivalent in this case. Now it turns out that if you switch your integration theory from Riemann integrals to something perhaps called Stieltjes integrals, then this becomes stronger, but in the context of Riemann integration, they are all equivalent. And really, this is the harder part. It's not too complicated to show that 5 implies all the other ones, but to go from any one of these to 5, it requires a little bit of work. Okay. So this probably is going to show up in problem set 8, I think. So with a couple more sort of equivalent statements. Okay. I want to add one thing. This is also very convenient, this sequential sort of characterization. So this one. There's a sequence such that the gap between the lower and upper Darbou sums goes to 0 along the sequence of partitions. For any such sequence of partitions, so in the case of 4, if I were to choose for each partition in my sequence one sampling function, if for any n S sub n is a sampling function for the nth partition, so that I have a sequence of Riemann sums, well, that sequence of Riemann sums converges to the integral. And also, the lower and upper Darbou sums too converge to the integral. Oh, not 0, of course. Should be the integral. This is also the integral. So even though Riemann sums are kind of awkward because you always need to take a sampling function, for computation purposes, I think it does become convenient to be able to switch between the two. Okay, any questions about any of this? I'm going to keep using these characterizations in what follows, but I'm going to leave it to you to verify them. And I think this and this are done in the textbook, but not the other ones. Okay, I should also mention, I had mentioned something called the net, which I said, oh, it's a more Smith sequence. It was a function whose input was an arbitrary directed set. And we had discussed how this IP of I is a directed set. So you can imagine that really, for instance, this tells you that the net, that is the gap between upper and lower Darbou sums, is a convergent net that converges to 0. So, aka the net that goes from IP of I into the reals converges to 0. You might also see some problems about net convergence, how it relates to continuity and other things in the next problem set. I was thinking of perhaps covering it a little bit more in detail, but it's going to be better, I think, for me to leave them to you. Okay. Any questions about any of this? Riemann integrals. Okay. And I need to check my battery because my batteries are getting older. In the morning I checked it and it was 100%. I didn't use the camera, and then now when I turned it on, now it's at 55%. So that's what happens, I guess. Anyway, so let's start with this. Any continuous function is Riemann integrable. Okay. Theorem. Any continuous function is Riemann integrable. Of course, not all Riemann integrable functions are not all of them are continuous. For instance, you can have piecewise continuous functions and stuff like that. You can, in fact, state something very precise about how much a Riemann integrable function fails to be continuous. And so that is what is called the Riemann-Lebesgue theorem. It says that any Riemann integrable function, or rather, any bounded function is Riemann integrable if and only if it is continuous except on a negligible set. Negligible has a very specific meaning there, which requires this Lebesgue integration somehow. So we're not going to discuss that. It's slightly more advanced than what we're aiming for in this class. Maybe in the future. But at the very least, we should be able to prove that any continuous function is Riemann integrable. Okay. So let f be continuous on the interval. And remember that I is a closed and bounded interval. Recall closed and bounded. We had discussed a certain property of continuous functions defined on compact subsets. And this was what is called uniform continuity. I didn't spend too much time on that when we were when we were first discussing this. So now I guess we have to prove this. But let me just say for now that I'm going to add the lemma in between the proof, and then I'm going to go with the proof of the theorem, and then I'm going to prove the lemma. Okay? So this is something that you end up doing all the time in math. It's like you're trying to prove something bigger, but then you realize you need some sort of auxiliary results. Okay? You sort of abstract that out, and once you have time and stuff, you can sort of cover this case as well. F is uniformly continuous. We're going to prove this in a second. Let's just assume that it is correct. This means that instead of saying that it is continuous at every point, you start with the epsilon, and then there is a delta such that for any 2 points, you have the delta epsilon thing. For any epsilon, there's a delta such that for any x and y and I, if the distance between x and y is bounded by delta, then the distance between their images is bounded by epsilon. This is, in general, something strictly stronger than continuity. But because the function is defined, we're considering a closed and bounded interval, we get to do this. Okay? I'm going to prove this in a second, but let's just assume that for now. And let's try to prove the fact that continuous functions are Riemann integrable, assuming this, and then we can cover the lemma. Okay. So what do I need to do? One of the characterizations of Riemann integrability tells me that if I can bound the gap between the upper Darbou sum and the lower Darbou sum using some partition, I should be good. Okay. Here's what I can do. Let epsilon be positive. Then there is a delta, as in here, such that for any x and y, if the distance between x and y is less than delta, the distance between f of x and f of y is less than, let's say, epsilon divided by the length of I, which is rho minus lambda. Okay. Now, if I can find a partition P such that the gap between the lower and upper Darbou sums of f is bounded by epsilon, I would be done. Okay. Certainly, I can take some partition such that any pixel of the partition has length at most delta by just, refining it. Such that for any pixel in my partition, the length of the pixel is bounded by delta. Okay, so now let me look at the upper and lower Darbou sums of this. So this is the sup of f restricted to p minus inf of f restricted to p times the length of p. Okay. Now, any pixel in my partition is itself a closed and bounded interval. F restricted to this partition, restricted to this pixel, is continuous. By the maximum principle, I know that this sup is in fact a max, this inf is in fact a min. Okay? Which means that this max is in fact of the form f of x for some x in my pixel p. And likewise, this min is in fact of the form f of y for some point y in the same pixel p. But by definition, the way I chose, the length of p is bounded by delta, which means that x and y is delta close, which means that the image, so the sup minus the inf, is bounded by epsilon divided by rho minus lambda. Okay, which means that this is bounded by epsilon divided by rho minus lambda. It's a constant. I can take it outside the sum. So this is bounded. Take this outside the sum to get this. But if I were to add up all the lengths of all pixels, this has to add up to the total length of the interval, which is just epsilon. Okay, yeah.
Can you run through how you bounded the supremum again?
Yeah. I wanted to sort of repeat again how to get this. And maybe we can also discuss how I came up with this partition too. That's sort of also somewhat abstract. So let's first think about this. So P is of the form lambda sub p, comma rho sub p. This is closed and bounded. F restricted to this partition is continuous. By the maximum principle, it attains its maximum and its minimum. In other words, there is an x and there is a y in P such that the sup of f restricted to P is exactly f of x, and its inf is exactly f of y. That's what the maximum principle says. Any continuous function on a closed and bounded interval attains its max and its min at least at some point. Maybe there are multiple x's and y's that does this, but there's at least one x and one y. Well, if that is the case, this guy, and I know that this is larger than this, or not less than this, which means that this is in fact an absolute value if you want. So f of x minus f of y in absolute value is exactly this guy. But because I chose my pixelation in such a way that each pixel has length at most delta, and since x and y has to be in the same pixel for any pixel, the distance between x and y is at most delta. Which means that by uniform continuity, which again I still have to prove, this has to be bounded by this number. Okay. Now, how do I get this specific partition such that this happens? After all, I have an epsilon, and this lemma tells you that there's a delta such that something happens. But how do I get the p such that each pixel of p has length at most delta? Any guesses? So
You could just travel, make each pixel delta over 2 length, and then just go until you reach the
yeah, you can do that. Another thing you can do is you can use the Archimedean property. Delta is a positive number. You know that, Well, there is, by the Archimedean property, you know that there's an integer, n, positive integer, such that 1 over n is strictly less than delta. That exists. There is an n such that 1 over n is less than delta. Then define your partition P to be this. Lambda to lambda plus n. Lambda plus 1 over n. And then lambda plus 1 over n to lambda plus 2 over n, and so on. All the way up to rho minus 1 over n, or maybe I should, oh no, that is not quite correct. I need to add the length. Okay, so let me not write down the formula for it. The idea is that once you have this n, what you can do is, you can look at the cut points. Yeah, so you're going to start with, oh, I think that was correct actually. So lambda to lambda plus 1 over n, and then lambda plus 1 over n to lambda plus 2 over n, and so on. All the way up to something, and there's going to be sort of like a greatest sort of multiple of 1 over n, such that lambda plus that greatest multiple times 1 over n is sort of right over here. And then the gap here, that means that is going to be even smaller, quite possibly. And so that's how we can, so there's like a remainder, if you want. Because you don't know necessarily that the distance between rho and lambda is divisible by n. Maybe it is not. But still you can sort of fill up, partition your interval in such a way that each of these pixels have length at most 1 over n, and maybe there is one that is of lesser length. So that's how we come up with this guy. One way of doing this, of course. There are multiple ways. Okay. So any questions about this argument so far? We still need to cover this lemma. It's not too complicated, actually, but we need to use some of the older properties that we had proved before. And so let me prove the lemma. So this is the end of the theorem. For the lemma, what we can do is the following. Say f is continuous, but it is not uniformly continuous. Say, so proof of lemma. Say f is continuous, but not uniformly continuous. That means that there is an epsilon 0 such that for any delta, right, there is an epsilon 0 such that for any delta, there are 2 points, x delta and y delta, such that the distance between x delta and y delta is bounded by delta, but the distance between their images is bounded by epsilon 0. I can choose delta to be of the form 1 over n. That would generate for me 2 sequences, x bullet and y bullet. In I, such that the distance between x sub n and y sub n is bounded by 1 over n, but the distance between their images is bounded from below by some epsilon 0. But I know that I is a closed and bounded interval. Bolzano-Weierstrass tells me that there's a subsequence of x bullet that converges to some point in I. Then, looking at those times, I can look at the subsequence of y bullet. Again, by Bolzano-Weierstrass, I can take a further subsequence of y bullet that converges to some point. This condition would tell me that these convergent subsequences have to converge to the same point in I, but by continuity, the images would be separated. this is the idea. Let me write it out because it is slightly complicated. So first I start with a subsequence of x bullet that converges. So it continues from here. By Bolzano-Weierstrass, there's a strictly increasing function j such that x prime bullet, which is defined as x bullet composed with j, converges to some point x prime infinity in the interval. Now, consider the subsequence of the other sequence given by the same sampling of times. This is a subsequence, this is a sequence in I. Applying Bolzano-Weierstrass to this subsequence, Bolzano-Weierstrass, there is a further subsequence, so j, maybe k. There's a strictly increasing function k such that y double prime, which is y prime composed with k, converges to, let's say, y double prime infinity in I. But then I can define x double prime to be x prime composed with k, so that this guy is a subsequence of this guy which converges, but any subsequence of a convergent sequence has to converge to the same point. Okay, I have two sequences in I. First, I sample the subsequence from the first one that converges to some point. That gives me a choice of times. That's what it means to take a subsequence. Then I use the same choice of times used in the other sequence. So now this is a subsequence of the other sequence. I don't know if this converges, but I know that by Bolzano-Weierstrass, I can further sample out a subsequence of this guy that converges to something. Okay? So I have the first subsequence choice and then the second subsequent choice. Then using this guy, I can look at this further subsequence of the first subsequence, which has to converge to the same point. But then, you see, the reason why I'm doing this is that if I were to compare x double prime sub n to y double prime sub n, ultimately, maybe I can write it like this actually. So, this really is x sub j composed with k of n minus y sub j composed with k of n, which means that this is bounded by 1 over j composed with k of n, but since j and k are strictly increasing, that's the definition of a subsequence, as n goes to infinity, this decays to 0, which means that their limits have to be the same. So the limit of this guy, which is x infinity prime, and the limit of this guy, which is y infinity double prime, have to be the same. But again, if I were to look at the images, by the continuity of f, this guy has to converge to f of this, and this guy along the subsequence, this subsequence, has to converge to the same point. So limit as n goes to infinity of f of x double prime n minus f of y double prime n is 0, which cannot happen because if I were to compare the values of f on the first sequence and the second sequence with the same times, their distance is bounded by epsilon 0, which is a positive number. That's a contradiction. Which means that there is no way that this function is continuous, but at the same time not uniformly continuous. And that's the end of the proof for the lemma. It's a contradiction. It's the end of the proof of the lemma. It really is not super complicated, even though when you first see these arguments, they kind of look complicated. Maybe they're a little bit technical, but in practice, the way you would say this is that if I were to take these two sequences in I, then up to a subsequence, I can assume that x bullet and y bullet converges, and then you would be done basically. But if you're trying to be more formal, you would have to be careful about the subsequences you're choosing. Okay. But that's that. Any questions about this? Okay, so at the very least, continuous functions are Riemann integrable. Not all Riemann integrable functions are continuous because, for instance, I can consider, here's a nice example actually. So we had these monomials, x to the n, defined on the interval. And then recall that when we were discussing uniform convergence and pointwise convergence of a sequence of functions, that was the example we were looking at. And we said that if I'm considering these functions to be defined on the interval 0 to 1, then the convergence is pointwise but not uniform. And this was the limit function. If x is between 0 and 1, 1 not included, 1 if x is equal to 1. Certain that this is not continuous. It has a discontinuity at x equals 1, right? But this is Riemann integrable, okay? Why is that? Because I need to compare the lower and upper Darbou sums. Well, the lower Darbou sum for any partition whatsoever is going to be 0, right? Because on any subinterval of 0, 1, the infimum of this function is in fact its minimum, which is 0, which means that this lower Darbou sum is always going to be 0. The upper Darbou sum is not going to be 0 because you're going to have at least one pixel over here, and for this last pixel, given any partition, its sup is going to be 1. So this is going to be, maybe let me write it like this. So sup of f restricted to p times the length of the pixel. And this is just going to be the sup of f restricted to to the last pixel here. Let's say p sub n. Or maybe just say p star. So the sup of f restricted to p star times the length of p star. This, because of this, is 1, which means that this is just the length of p star. So the upper Darboux sum is not necessarily is not necessarily equal to 0. But I claim that even though that is the case, this is fine. That is to say, the gap between the lower and upper Darboux sums is going to decay to 0. Why is that? Because I can take the sequence such that each cut point is at one multiple of 1 over n, in which case this would be exactly 1 over n. And as I take n to infinity, even though the upper Darboux sum is a positive number, it's going to decay to 0. Which means that the Riemann integral of this guy exists. In other words, this function is a Riemann integrable function, and its integral is 0. Okay? So this is an example of a continuous. This is an example of a Riemann integrable function that fails to be continuous. Okay. I'm out of time, so we're going to finish for today. We're going to continue on Friday. Thank you. Let's start. Good morning. Last class before the break. We're not going to get to the fundamental theorem of calculus today, unfortunately. So we're going to be doing that once we get back. Because there's still a couple of sort of theorems that are more or less independent from the fundamental theorem. But still, it's good to know, and I don't want to switch the order in the textbook too much. So last time we talked about how a continuous function on a closed and bounded interval is Riemann integrable. We had used this idea that any continuous function on a closed and bounded interval is uniformly continuous. And so that allowed me to sort of handle these partition business and get a nice upper bound on the gap between the upper Darboux sum and the lower Darboux sum for a partition that is sufficiently small in, let's say, size. In other words, whose pixels are small. So here's another theorem. If I have a bounded function that is monotone, so non-decreasing or non-increasing, then f is integrable. So it doesn't need to be continuous. So I'm just going to assume without loss of generality that f is non-decreasing. There's also this other case of non-increasing f. I'm just going to leave that to you. Okay, well, one of the characterizations of Riemann integrability was that if I can find a sequence of partitions such that the gap between the upper Darboux sum relative to the elements of the partition, of the sequence, minus the lower Darboux sum goes to 0. So, I want to show that f is an R, the set of all Riemann integrable functions. And for this, it suffices to find a sequence of of partitions such that u minus L relative to this, the elements of the sequence, goes to 0. Such that the limit as n goes to infinity of u of f, comma, curly p sub n minus L of f, comma, curly p sub n is 0. Okay, well, I'm going to take the sort of obvious choice perhaps, which is for Pn, p sub n, I want to have my pixels to have length 1 over n. Fix an n and define p sub n in the following fashion. First, I want to draw the picture so that I can understand what is going on. So the left endpoint is lambda, right endpoint is rho, and I want each of the pixels. Either I'm going to choose each of the pixels to have size 1 over n, or another thing you can do is you can say, oh, I'm just going to have a pixelation, a partition, each of whose pixels have the same length, and you want this length to decay with n, so as n goes to infinity. So what you can say is that my first cut point is going to be lambda plus rho minus lambda divided by n, and then my second cut point is going to be lambda plus 2 times rho minus lambda divided by n, and so on. So that each of these pixels have length exactly 1 over n times the length of the larger interval. And so here's what you can write. So lambda to lambda plus length of I, which is exactly rho minus lambda, divided by n. That's my first pixel. And then my second pixel is going to be lambda plus L of I divided by n to lambda plus 2 times L of I divided by n, and so on. And then the last one is going to be lambda plus n minus 1 times length of I divided by n. To rho. Of course, rho itself is exactly lambda plus length of I. Okay, so this is my partition. Okay. And so if I were to look at the gap between the upper Darboux sum of f and the lower Darboux sum of f relative to the same partition, I want this guy to decay to 0. Okay. So this is going to be a sum over pixels of the sup of f on each of these elements of the pixelation times the length, and then I'm going to be subtracting the inf. And so these are finite sums, which means that I can consolidate and write this difference as just one sum. And in fact, I can just use some indexing. So I can think of this as I goes from 1 to n, okay, sup of f of x, where x varies maybe I can write it like this. Before going into this, let me abbreviate this stuff. It's going to be easier to see, I think. So I'm going to call the ith pixel of the nth pixelation p sub n comma I. And so this is going to be of the form lambda plus I minus 1 times the length divided by n, comma, lambda plus I length of I divided by n. Okay, so this is the ith pixel of the nth partition. Yeah, so for instance, this is p sub n comma 1. When I equals 1, this is just 0. So this gives me lambda. And when I equals 1, this just gives me this. Okay, so this is the ith pixel of the nth pixelation. Okay. In abstract, so when you're sort of defining things in abstract, it's somewhat inconvenient to write the endpoints, but when you're trying to compute things, it's often good to sort of have some logistics as to how the indexing should go. So now I can write it like so. Nth pixelation has exactly n pixels, so I goes from 1 to n. Then I'm going to do sup of f restricted to the ith pixel minus inf of f, again restricted to the ith pixel, times the length of the ith pixel. But the length of the ith pixel is exactly, so this minus this, which is exactly length of I divided by n. Okay? Now, in the summation, this factor is constant in I, so I can take it out. And write it like this. Now, what is the next step? How can I continue? After all, I'm trying to bound this. If I can say something about this, I would be done, because this guy goes to 0. So which assumption did we not use so far? We haven't used something.
It's non-decreasing.
Exactly. If f is non-decreasing, certainly on each of these pixels it is non-decreasing, which means that if I were to take one of these pixels, and if I'm restricting my function to this pixel, its sup has to be this endpoint, or it's the value of the function at this endpoint, and its inf has to be the value of the function on this endpoint. Okay? So now I can plug in those values. Let me continue from, let me continue from there. So that sum over there is equal to the length of I divided by n times the sum where I goes from 1 to n. The sup of f restricted to this pixel has to be f of the right hand point, because f is non-decreasing. Okay, so this is f of lambda plus I, length of I divided by n, minus its inf is going to be f of this value. So I'm summing over these guys. This is nice because this is telescoping. That's the idea, okay? Because I'm adding up all terms of the form where I goes from 1 to n, and then I'm subtracting all terms of the form. Again, it's the same thing, but now, if you want, this goes from 0 to n minus 1. Maybe I can write it out explicitly. So I have this factor. Then I have f of lambda plus L of I divided by n plus dot 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 plus f of lambda plus n minus 1 times L of I divided by n. This is this sum written out explicitly minus, now I have to start from lambda, you see, minus f of lambda minus f of lambda plus L of I divided by n minus dot 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 all the way up to this factor being n minus 1. Of course, this should have been n here. Just leave it like this. Minus all this is multiplied by this factor. The point being that this is going to stay, but you see, this is going to cancel out with this. And so on, all the way up to this last factor in this sum. It's going to cancel out with this guy. So that at the end, I'm going to have this minus this. But of course, this is nothing but lambda plus length of I, which is exactly equal to rho, the right endpoint. So this is length of I times f of rho minus f of lambda divided by n. This is a finite number, which means that as n goes to infinity, the gap here that I was trying to bound goes to 0, which means f has to be integrable. Okay. It's like the proofs are not really that sophisticated, but you have to sort of like bite the bullet and start writing things out explicitly, then sort of things sort of start working out. Okay. Any questions about this? I'm going to leave it to you as an exercise to verify the linearity properties. In other words, if I have two functions that are integrable, then certainly their sum should be integrable as well, and their Riemann integral, so the Riemann integral of the sum should be the sum of the Riemann integrals, and likewise for a constant multiple. Exercise. If I have two Riemann integrable functions on this closed and bounded interval and a number, then the function that is the sum of the two functions is itself Riemann integrable. And the natural formula, which is the integral of the sum is the sum of the integrals. And C times f is again Riemann integrable. Constant multiple of any Riemann integrable function is Riemann integrable. And of course, you should be able to take out the constant out of the integral. In a sense, if we didn't have these properties, if integration was not what is called a linear transformation, this whole theory would be sort of for naught. It's like if the sum of the functions, or rather, if the integral of the sum is not the sum of the integrals, that integration is not a good theory, okay? So this is like one of the sort of starting points. And really, if you want to be sort of like more abstract, from a more abstract point of view, you would say, here's a certain class of functions that I would want to be integrable. And integration is going to be a linear transformation of functions. If you have taken linear algebra, this says really that the set of all Riemann integrable functions is a linear space. It's a vector space. And integration is a linear transformation. Is a vector space, and the function that takes a Riemann integrable function and sends it to its Riemann integral is linear. It's a linear transformation. Of course, this is what is called an infinite dimensional space in a sense. So you cannot really think about this Riemann integral itself, even though it's a linear transformation, you cannot really think of it as a matrix. I mean, in a sense you can, but it takes some work, is what I'm trying to say. Under certain circumstances, you can certainly think about the integration here as a matrix operation. Okay, but we're not going to get to that because not really the main point of this class. Okay. Any questions? Now, I would like to say something about the monotonicity properties of this operation that takes a Riemann integrable function and sends it to its Riemann integral. I would like to be able to say something like, if I have two functions, f and g, such that g always dominates f, then certainly the same thing should hold for their integrals. Okay? In other words, if I were to take a Riemann integral and change the integrand, the thing inside the integral here, by something larger, the value of the integral should increase, or at least not decrease. Because ultimately, we would like to be able to start bounding integrals as well. And so the theorem says the following. If I have two Riemann integrable functions such that one of them dominates the other one, then the corresponding Riemann integrals are in the same relation. That is, if I have two Riemann integrable functions such that for any x and I, f of x is bounded from above by g of x. In other words, you can think of it as, oh, the graph of g is always above the graph of f. Certainly the area underneath this guy should be larger, right? Then this is the case. And I should also mention, sometimes I don't write this f of x inside the integral because I'm sort of like being lazy. But if you want to be like more formal, you probably should be writing f of x. That's, of course, the dummy variable, so to speak. Once we get back from the break, we're going to talk about this change of variables. And under certain circumstances, you can sort of like even do a change of variables, so to speak, change your letter, your dummy variable, in such a way that the integration becomes nicer. But we're going to get to that later. So here's the proof. Certainly, if I were to do this, let me define phi to be the difference, g minus f. Well, this is a linear combination, they would say, of these two functions. So because g is integrable, minus g is also integrable. Or rather, because f is integrable, minus f is also integrable. And then I can add g and minus f to get yet another integrable function, which means that this is Riemann integrable. And its Riemann integral is precisely the Riemann integral of this guy minus the Riemann integral of that guy. By the previous theorem, by the exercise. And so it suffices to show that the Riemann integral of this phi is non-negative. Of course, we also have the fact that because g of x is always greater than or equal to f, phi of x is always non-negative. So it suffices to show that the Riemann integral of phi is a non-negative number. Which in a sense is very obvious. It's intuitively, it should be true, because I have this phi, I'm saying that its graph is always above the x-axis. And so if I were to integrate it, certainly this integral cannot be a negative number, right? But we need to prove it. Well, I know that, you see, phi is already Riemann integrable. So I don't need to worry about both the upper and lower Darboux sums. If I can bound the lower Darboux sum of this function, this would be sufficient to show that this guy, this holds. So the Riemann integral of phi is certainly bounded from below by the lower Riemann integral. Recall that this was by definition the best lower Darboux sum, where curly p varies in the set of all finite interval partitions. But then this is non-negative, because given any partition, well, this is by definition the sum over all pixels of the inf of phi restricted to the pixel times the length. This is a positive number always. And this, because phi is bounded from below by 0, it might be bounded from below by something larger, but at the very least it is bounded from below by 0. This is non-negative. So I'm adding up finitely many non-negative terms. which means that this has to be non-negative. If I have one partition such that this happens, certainly the soup over all partitions have the same property also, and that's the end. Okay? Not very complicated, really. I'm just rearranging terms in a sense. The main problem, the main difficulty with integral calculus is the formalism that you end up needing to sort of keep using. Okay? So for instance, this is why I left that previous exercise to you. The integral of a sum is the sum of the integrals. It's like there, I'm actually asking you to fight against this intuition that you have so that you can sort of prove things, even though you know that it should be true. Any questions? Okay, now let's apply this situation to a very nice result. This is very convenient, it's very useful. It says something about what happens when you take a Riemann integrable function and instead of looking at the function itself, you look at its absolute value. Okay? So theorem. Maybe I should write it here. It's better. I have one Riemann integrable function, f. The first part of the theorem says that its absolute value, 2 is Riemann integrable. And the absolute value of the Riemann integral of the original function is bounded from above by the Riemann integral of the absolute value of the function. Okay? Now the second part immediately follows from the previous theorem insofar as we can show the first part. So let me just put that aside. Well, certainly this is true, and I'm assuming part 1, which means that by the previous theorem, the integral of this guy has to be bounded from above by the integral of this guy. But in fact, f itself bounds from above the absolute value of the function with a minus. This is always negative, this is always positive, and f varies between the two, which means, again, by using the same theorem, I have that this is the case. But then I can take out this constant -1 to the outside by the previous exercise, by this exercise of linearity and linearity. So this now becomes minus integral of f of x in absolute value, but then saying that this value is bounded by this non-negative number and it's negative is literally the same thing as saying that its absolute value is bounded from above by this. So this is the end of the second part. We need to show the first part. How do we show that f in absolute value is Riemann integrable? Okay. Let's see. Any ideas as to what would work nicely in this situation? We can try using the definition, of course, or we can use one of the characterizations of Riemann integrability. Somehow, ultimately, we need to use Riemann integrability of f itself as a leverage, right? That's the only thing we have in this situation. Let me think. Well, I mean, at the very least, we're going to have to start with a partition. Oh, okay. 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 So, now this guy, I'm just using the original function. This is the lower Darboux sum. So I'm taking the sum over all pixels of inf times the length of the pixel. Okay. So if I were to take the absolute values of these, and if I were to take the absolute value inside, that sum would possibly increase. But then I'm taking the absolute value of absolute value of the product of two numbers, but this is always positive, which means that I don't need to write the absolute value here. I can just write it like this. Now, how to relate the absolute value of the inf to the inf of the absolute value? So let's test it out. So what is this about? I have basically a set. Maybe it has negative values somewhere here. But then I'm taking the set consisting of all absolute values. So for instance, let's say that my function f on one of these pixels is constant, and it is -1. Okay. So that its inf is also -1. But then if I were to take the absolute value, this becomes +1. Okay. But this is the same thing as first taking the absolute value of the function, in which case it would be just 1, and then taking inf. So it looks like, without any sort of issues, I should be able to put this absolute value inside. Okay. So this is what is at stake. Maybe I can write it on the side. This, after all, is just taking the inf over a certain subset of reals. I have a subset of the reals, and then I'm defining the new subset B as A in absolute value, where A varies in uppercase A. I'm trying to relate inf of B to the inf of A. Right? That's what's at stake. If I can say that they're equal, then that would be very nice. Yes?
They're not necessarily equal.
Okay.
If A goes from like -100 to like 5, then absolute value of A goes from and includes 0. Then absolute value of A goes from like 0 to 100. Where if your infimum's magnitude is larger than your supremum's magnitude.
Say again. What is your?
A is, say, an interval between like -10 to 5.
Okay.
And the absolute value of A is an interval from 0 to 10. Like running
You're right.
absolute value on all of things.
You're right.
In which case, it breaks.
Okay, so you're saying that they're not equal. So the inf of this is not the same thing as the inf of this.
Yeah.
Right? Because the inf of this, or rather the absolute value of the inf of this is not the same as this.
Yeah.
You're right.
In that case, it does mean that the absolute value of the inf of that is the supremum of the new set. Like when it breaks, but that doesn't help very much.
Mm-hmm. Oh, okay. I have it now. You're right, they're not the same, but if I were to put the absolute value inside, this is going to increase, okay? And here's why. I guess this was misleading because we're comparing the two functions. So comparing two functions is not the same thing as comparing their images, in a sense. Because when you're comparing two functions, you're biasing the vertical distance. Okay? So here's the idea. Sorry for this, I'm just blanked out. So I claim that this is what's going to happen. Which of course is nothing but the lower Darbou sum of the absolute value. So I need to justify this. We need to figure that out. And here's the justification for this star. Certainly this is true. But then if I were to take the inf of this as x varies over p, this is going to possibly decrease. Okay. So first I realized for any x in this pixel, f of x is bounded from above by f of x in absolute value. And then I realized if I were to look at the inf of all of these values, this is going to decrease quite possibly. So I have a number that doesn't depend on x. But then that means that this value is a lower bound for all possible values of the absolute value of f, which means this is the case. Okay. But then, how do I get the absolute value here? Well, this is always a non-negative number, because it's the inf of something that is bounded from below by 0. Which means that if I were to replace this by its absolute value, it's not going to matter. I can again do this. Okay, that's how we get this. I think that is true. Yeah, I mean, I can do that, or I can. Now I'm questioning this actually. Okay, let's look at the textbook. In the textbook, instead of just looking at the lower Darbou sum, yeah, I guess it does make sense, because like even if I were to bound this absolute value of the lower Darbou sum, how am I going to relate it to the integral of f? So I guess maybe it's good to just look at the difference of upper and lower Darbou sums. Okay, maybe this is not correct actually. I'm blanking out right now. Every semester there's like a class like this where just doesn't work. Something doesn't work. Okay, so let's instead look at this. Let's look at the gap. Yeah, so somehow if I can do something about, if I can relate the gap for the absolute value function to the gap of the original function, I would want something like probably this. If I can do this, then by taking the partition to be smaller and smaller, I can, so this I know goes to 0. That means that I would be able to show that this also goes to 0, which is equivalent to saying that f in absolute value is Riemann integrable. We're going to do this when we come back. I don't want to make you stick around longer than you need to. Thank you. Have a nice break, and I'll see you in 2 weeks, I guess.